My name is Jaylin Herskovitz, and today I'll be presenting our paper XSpace, an augmented reality toolkit for enabling spatially aware distributed collaboration. How we interact with our environment can provide rich contextual information about our intents, needs, and actions that facilitates effective communication between individuals. For example, in this clip, because the person is standing near the board, I might assume that they are about to add another sticky note to the list. Prior research has summarized many benefits of shared spatial environments for collaboration, even if they are virtual, including creating a persistent context for ongoing activity, enabling a peripheral awareness of others, facilitating chance encounters, and allowing for natural interaction with virtual content. In order to achieve these benefits, a variety of prior work has focused on developing AR systems to support distributed collaboration. For example, holoportation, a system for capturing and displaying live 3D representations of a person, represents a state-of-the-art system for distributed AR collaboration. However, distributed AR applications that incorporate users' environmental contexts are still incredibly difficult to design and develop. And more specifically, we see a lack of tools to help developers explore and implement the rich variety of environmental sharing scenarios that we see in experimental systems. Thus, the goal of this research is to make that process more approachable through a toolkit to support these applications. Our approach to addressing this consists of three main parts. First, based on a literature review of existing virtual collaboration tools, we characterize the design space of creating shared virtual spaces from two or more physically distributed environments. Next, we designed and developed XSpace, a toolkit to integrate the operations we identified into existing AR applications to enable distributed multi-user functionality. Finally, we demonstrate how XSpace can be used to support a variety of applications by implementing promising application scenarios that are difficult to produce currently. Here's a preview of what an application created with XSpace could look like from the AR perspective. Here, a portion of the remote user's environment is overlaid onto the physical, giving the user additional context for what the remote user is doing. Now, I'll go into more detail about the methods for sharing environmental context that we identified. In order to explore the design space of creating shared AR spaces involving multiple environments, we reviewed a variety of existing sources, including existing AR/VR commercial applications, previously published research, and existing AR/VR developer toolkits. From this review, we distilled three primary methods of blending physical environments to create a shared virtual space. Each of these methods centers the collaboration around a different spatial aspect for coordination and alignment. First, object-based methods use physical objects as reference points for shared virtual content. We call these shared anchors. Second, perspective-based methods provide a view into a remote space. Portals and World in Miniature are two examples. Third, mesh-based methods use operations on scanned environmental meshes to overlay remote spaces onto the physical. Next, I want to show some illustrated scenarios for two of these methods to demonstrate how they might be used. First, I'll talk about the shared anchors method. So let's say I have two users collaborating across these spaces, a living room and a smaller conference room. One option for sharing AR content is to use the table as a single shared reference point for all of the virtual content in the space. This works okay when you have content constrained to the table, but when you start to add other elements, issues can arise. For example, I would start placing user avatars relative to that anchor point as well. But if the user in the living room sits on their couch, in the conference room they would appear to be clipping through the wall. Instead, multiple objects are used as reference points for content. So here, the tables are mapped to each other, the couches in the living room are mapped to the chairs in the conference room, and a TV on the wall is mapped to a whiteboard. Once those pairings are defined, virtual objects can then be placed relative to all of those anchors. I'll show another illustrated example of the mesh overlay method. Let's say I have one user working from their desk and another working from their dining room table. However, the user at their desk doesn't have a lot of table space open. We imagine that their desk could be virtually extended by overlaying the dining room table on top of it in AR, so essentially merging the two objects together. In this way, each user has direct access to parts of the other user's environment, can interact with it, and can see how the other user interacts with it. To support the methods for creating shared AR spaces that we identified, we developed XSpace. XSpace provides an infrastructure to turn single-user AR applications into ones that support distributed collaboration through various compositions of the space alignment methods. XSpace consists of three main components. First, XSpace's developer toolkit allows developers to add shared space configurations to existing AR applications. Second, XSpace's server provides an architecture for multiple AR devices to share environmental information. And finally, a web interface with a set of visual design tools allows developers or designers to simulate different space configurations on real or synthetic environmental meshes. I'll give a short walkthrough of how developers and designers can make use of these components when creating their applications. First, developers create their AR application as normal, making note of what AR content needs to be shared later on. Second, developers can use XSpace's visual tools to preview a variety of configurations on synthetic meshes to figure out what works best for their application. Next, developers integrate XSpace's components into their Unity application. We aim to make this as simple as possible. Take this function for throwing a snowball object as an example, where I instantiate a snowball object and then add force to throw it. When throwing the snowball, developers just need to share the desired parameters, in this case, position and direction, with XSpace's server. For other users to see the snowball, they retrieve the parameters from XSpace's server, automatically translated into their local coordinate system based on the chosen space configuration. Finally, when developers run their applications, they can then return to XSpace's visual tools to reconfigure the shared space with the real-world scan data. They can then see shared objects and user avatars in the visual tools being updated in real time. In this way, developers can quickly debug and test various space configurations directly as their application runs. Next, I'll show how XSpace's visual design tools can be used to configure shared spaces. Here, the yellow and blue meshes each represent a separate user space. XSpace's visual design tools generally consist of a configuration panel where alignment methods can be applied to scanned environmental meshes by directly editing a 3D scene, and a simulation panel where a first-person AR view of the resulting space is simulated in the browser. To configure a pair of shared anchors in XSpace's interface, users first draw a bounding box around the relevant portions of each environmental mesh. Then, in the simulation panel, we can see that avatars and objects are then positioned relative to that anchor. When adding a portal, it will initially appear in a default location in both spaces. Users can then edit the position and orientation of each portal using transform controls. After confirming the position, the portal appears in the simulation interface. Similarly, a miniature version of one environmental mesh can be placed inside of another space. After confirming, the simulation panel shows updated avatar locations in relation to the miniature mesh. So here, I can see the user inside the miniature mesh, walking around and looking up at the other user. Finally, users can directly manipulate meshes in order to create a shared area where each mesh will be directly overlaid onto the other. After drawing a bounding box around the area to be shared, the simulation view will then show the remote mesh being overlaid onto the local mesh. Objects are then placed relative to the mesh geometry. Finally, in order to evaluate XSpace's coverage and flexibility, we select three common single-user XR applications to extend with XSpace to support multiple distributed users. Each of these three applications implements a different technique identified in our design space, and I'll show two short demos. First, we implemented a multiplayer game where users launch projectiles at each other, similar to paintball, that uses the mesh overlay technique to create a shared play space with furniture for dodging throws or hiding behind. Upon opening the HoloLens application, users first scan the areas of their room that they wish to share. The scan is then uploaded to XSpace's server and is loaded into the visual design tools. Developers then configure the space to test it. So here, a user is specifying a region for the overlay around this couch and coffee table. The remote mesh then appears overlaid on top of the physical space, and avatars move around relative to the mesh geometry. Users can throw snowball projectiles that collide with each other or objects in either environment. So not only can these users interact with each other, they can interact with each other's environment and both see the same rendered effect of the snowball exploding. To show another example, Room Design is a collaborative furniture layout application that we developed as a web simulation of AR. After placing the miniature mesh, users can add furniture objects to the space and pass them into the miniature space in order to arrange furniture from a top-down view. We also highlight opportunities for privacy to be considered in this type of application. Because prior applications do not share users' scanned environment, it's totally possible that users will not feel comfortable doing so in all collaborative situations. We imagine that using our operations, users could have an additional level of control about the level of access that a shared space has, similar to the settings on a Google Doc. For example, this image shows a simulation view of an overlay between two spaces. We can see a light boundary around the shared space. If the user wanted to make this space more private to other users, they could then change the material of that boundary, perhaps making it more opaque. We also imagine that with the sharing of environmental information, physical objects could be used as proxies for privacy settings. For example, a user could do things like touch a light switch to turn a shared area on or off, or close their window blinds to open or close a portal. Building off of our work, we also found opportunities for future evaluation and study. One important direction would be to further study how AR designers and developers would conceptualize and work with the operations that we presented in order to create new and interesting applications. Another direction would be to work towards automating the methods that XSpace uses to link environments based on the mesh data alone. And finally, we believe that XSpace could be used as a future research platform to compare collaboration behaviors under different sharing conditions. Overall, XSpace is an important step towards creating more immersive and effective distributed AR experiences by leveraging users' local environments.